The next talk about lattice gauge series by Norman Christ. Let me say a few words. Norman is a professor at Columbia University. He made his PhD supervised by T.D. Lee. So once I have to ask him privately how the supervision was. And in the years 66 to 1980, he worked mainly on deep inelastic scattering, monopoles, instantaneous anomalous symmetry breaking, as most of the theorists. I mean, it's many people did that. And after 1980, he started on lattice QCD and to make realistic large-scale calculations. Large-scale means he needs an enormous amount of computers. So correctly, he thought that he should get developments on large parallel computers, which he did up till the year 2012. In fact, he built himself with some colleagues these computers. I think that's marvelous that a theorist is doing some hardware to make the calculations faster and better. That is really great. And for that, he got with his colleagues the Gordon Bell Prize for an optimum price-performance ratio. And that prize he got 98. Now, the last decade was reserved, if you want, and was focused on more accurate standard model prediction, mainly for rare processes. And the use of supercomputers then continued, but now he went to industry also, giving his idea to industry. I don't know which, will not tell you which industry, and so really large calculations can be done. Okay, can we welcome Norman Christ? His title is Lattice Gauge Series with supercomputers.
Well, thank you very much for the introductions. I'm indebted, obviously, to Brian and Glenn for the opportunity to give this talk. This is not intended to be a sort of general survey of lattice QCD, but a little bit more idiosyncratic, discussing some of the things that I've been interested in, but hopefully giving you an idea of where we now stand with this, well, now not so new technique. I would start a little bit by reminding you of the path integral approach to QCD and the non-perturbative approach to quantum fields, a little bit of a historical overview to give you some notion of how far the field's advanced and what we can do right now. I'd spend a very short amount of time talking about technology which drives lattice QCD, but is to some degree driven by it, and then talk about the present and future, very physics-oriented, the physics of QCD, where of course lattice methods let you study QCD, a really active topic in nuclear physics, as the earlier talk today suggests. But then it's also, of course, a critical component of many important standard model quantities, and the more accurately we can deal with non-perturbative phenomena, the physics of quarks and gluons, the more accurately we can test the standard model. So I would talk about three subjects: the hadronic corrections to mu and g minus 2, the indirect CP violation and k to pi decay, and the k long, k short mass difference as important quantities in the standard model that we can, with increasing accuracy, discuss using lattice methods. So starting out with lattice QCD, we're of course working on, well, I couldn't quite manage a four-dimensional lattice here, but we start out with a four-dimensional space-time lattice. The quarks take values at each of the sites, and the links provide a SU3 parallel transport between one site and the next. This is a theory that's formulated non-perturbatively by looking at a path integral of this sort. So we're integrating over the explicit gauge degrees of freedom, a little SU3 matrix for each link. And the fermions are represented not as Grassmann integrals, but integrated out and replaced by a large determinant. For zero baryon number. This is a positive definite integral, so we can evaluate it very successfully with important sampling techniques. So the methods of Metropolis and Feynman from the late 40s actually make non-perturbative evaluation of this path integral numerically quite possible. So this is a little picture of a hybrid combined molecular dynamics and Langevin evolution, which we follow in gauge space to ultimately have an equilibrium distribution of gauge fields distributed according to this weight, and then we simply average whatever quantity we're interested in computing over that ensemble of gauge configurations. So this is a theoretically rigorous approach. Of course, we have to take the limit, the continuum limit where the lattice spacing goes to 0, and the lattice problem is defined at that lattice spacing. We specify the lattice Lagrangian, and in the limit of small lattice spacing, we should be in the asymptotic freedom regime, and so we should be able to use perturbation theory to describe the short distance formulation of the theory, which means we really know what the theory is at the scale that we're formulating it. In fact, we sort of work it backward. We adjust the coupling constant on the lattice scale so that the lattice scale is in fact small, and then only when you go to larger distances do you see the stronger coupling, the non-perturbative effects taking over. So the small lattice scale needed to have discretization errors small also implies that we're working in a regime where we actually know what we're doing. It's a quite kind theory in terms of discretization. The cubic symmetry of a lattice and gauge invariance implies that all the terms that we might worry about appearing because of our discretization are all either break gauge invariance or have higher dimension. So there's no fine-tuning needed here. All we have to do is to make the Bayer coupling small, and we'll be doing a more and more realistic calculation. We might try to adjust the lattice action that we use to make this limit come more quickly, but basically, on some level, we can't go wrong. This is, of course, not the solution to all problems. First, it's a numerical calculation, so it often doesn't really provide insight into your results. So, well, we'll get a number, but we don't necessarily understand what's going on. We're also doing a kind of unpleasant numerical work. It's not like following the motion of the planets around the sun for 100 million years. This is all very statistical. You have to, just as if you were doing an experiment, deal with the fact that you don't have a precise answer. There are possible long autocorrelation times and various subtleties associated with doing a Monte Carlo calculation accurately. We are also, of course, start with the normal Schrodinger quantum mechanics, but instead of expanding into the Heisenberg picture, we expand into a Euclidean time, and so we're working with the time dependence, which is not physical. So if you wanted to know an answer to a scattering problem, for example, or a transport problem in a heavy ion collision, we would have a hard time with it because we're really working in Euclidean space and only kind of peeking over the edge at Minkowski space. A lot of the developments in the theory are actually learning how to get more information that's relevant in Minkowski space without actually working there. And of course, this fermion sign problem, which is a great difficulty for condensed matter physics and chemistry, is also true in lattice QCD if we choose to work with a non-zero baryon potential, baryon chemical potential. So doing the QCD phase transition at non-zero chemical potential is really, at the moment, very hard with lattice QCD. This also shows up if we try to study baryons. If you think about the modulus squared of the quark propagator in Euclidean space, this is actually the pion propagator, so it falls off relatively slowly. On the other hand, if you take a lot of those propagators, 3B of them, if you had B baryons, and you ask how fast they fall off really rapidly. The nucleon is much heavier than the pion. So in fact, the thing that's being averaged here is much larger than its average. So there's a very large noise problem, which you could easily view as another version of this sign problem. So historically, obviously Ken Wilson would be, well, so unfortunately he's not here. He invented the subject, and we're following in his footsteps. There was a while when this was a really analytic topic where people were looking at the strong coupling approximation, but fairly quickly, and much because of Ken's orientation, this was recognized as an opportunity for large-scale computing. Mike Kreutz produced this beautiful plot where the string tension actually behaved as a function of a lattice spacing in the fashion that the renormalization group predicts. So one had a pretty clear idea that this was working. By 1990, sort of 10 years later, one was moving beyond the quenched approximation and doing the full calculation, including the fermion loops. In 92, the fermion doubling problem was solved by this domain wall or procedure that Kaplan invented, or Neuberger's overlap version of it. And this was being routinely used in lattice calculations. These chiral quarks is my phrase for quarks that have real chiral symmetry and yet have the proper number of them. So the difficulties of the doubling problem are gone. And by 2014, the computing resources had reached the point where one can routinely work with physical quark masses. So at the present day, we can work with physical quark masses. We don't need to use chiral perturbation theory to extrapolate to the physical point. In fact, we now take an interest in chiral perturbation theory on its own right and try to see how well it works at physical quark masses. We can work with chiral quarks. We will typically work, or certainly if necessary, work on rather large volumes, 10 to 6 Fermi cubed, and relatively small lattice spacings. For the work that my collaborators and I do with chiral quarks, we are typically in a good region for finite lattice spacing errors associated with the QCD scale, but the charm quark is still a little heavy, and unless we start using an effective theory, we can't do a straight-up calculation with charm quark propagators. Maybe 15% is a little bit large, but certainly we'll have 5 or 10% errors that we have to deal with. So a very short discussion of technology. The place to start is that lattice QCD is enormously dependent on technology. All of these advances that I've been describing are partly clever algorithms, really good ideas that are invented, but most of these good ideas are not really practical unless you have a much bigger computer to run them on. So there's a real synergy between advancing computing strength and new ideas. A typical calculation that we're doing now is on a 64 cube by 128 lattice. This involves a stochastic integration over 1 billion variables. If we include the spin-a-half quarks in this determinant, well, first, it's not a 4D volume of this size. There's an extra factor of 12 typically. It's 5 dimensions. And so that means that when we talk about the integrand, the determinant that represents the quarks in the integrand, we're actually weighting this integral over 1 billion variables with a determinant of a 10 billion by 10 billion matrix. This is something that is actually quite straightforward to do. It just requires some stochastic methods. We're sort of in the thermodynamic limit in some sense. In fact, it takes a typical calculation here could easily be done with maybe 40 or 100 samples. There is so many degrees of freedom in each of these samples that we can get a 1% accuracy without actually averaging over that many different configurations. This is the mirror machine, a BGQ machine at Argonne, where we're currently getting most of our physics results from. And this is capable, in fact, for our code running on a little more than half of the machine, this will do 10 to the 15th adds and multiplies a second. So it's 1 petaflops sustained performance. And future opportunities are only limited by computing power, and if the US continues to compete with the Chinese on computing, this would be very well funded in the US, and there'll be lots of opportunities. So this, among all the different activities the DOE supports, this is among the richest, and so there certainly is a very, very real plan on which we're putting a lot of effort that will yield 1 exaflops computer, another 10 to the 3 in 2021. And well, we'll be able to do things more accurately, perhaps even by a factor of 10 with that boost in performance. To spend a little bit of time looking at our old exercise in hardware. This is kind of fun. It's in 1980, a colleague of mine, Paolo Franzini, when he learned we were interested in these things, encouraged us very much to build our own equipment. You could buy these very large-scale integrated chips that would do adds and multiplies, provided you could connect their legs to other chips. And also at this time, parallel computing really wasn't available commercially, and yet for a big lattice of identical regions, it's pretty trivial to imagine doing that problem very effectively in a parallel fashion. So certainly from maybe 1985 through maybe 2000, or a little bit later, there were many QCD machines built in the US, the UK, and Japan that took advantage of these facts. I'll mention in a moment our QCD on a chip computer, which was actually the model for the Blue Gene machine that I showed you a picture of earlier. Of course, at some point this becomes too hard for a little academic exercise. In 1993, we could get a QCDSP chip, a gate array designed with a non-recurring engineering cost of $300,000. By 2003, this had reached $1 million, and only by collaborating with relatively rich colleagues in the UK were we able to pay for that. The Blue Gene machine, I think, is in the order of 50 or 100 million for just the design of the chip. And I believe now you probably need $1 billion if you're going to design a competitive chip. And of course, if you're not using a competitive chip, there's not much point in working on the hardware side of things. This is sort of amusing. Some of you might remember Byte magazine. This was the professional journal in which we published the first article about our computer. This looks like a super scientific achievement cover of Science magazine. It's actually not quite so great. It turned out that the editor who commissioned the article had the idea that perhaps he could kill experimental high energy physics if he got it replaced by computer simulation. So we were being promoted for sort of the wrong reasons. These are the two large machines we built at Brookhaven. This was quantum chromodynamics with digital signal processors that we finished in 1998. This is a pretty large machine. And this, quite a bit bigger, is the QCDOC machine. This was done in collaboration with IBM. They, for this $1 million, agreed to make our chip for us, which was not trivial. It was some significant opportunity cost for them. At any rate, probably the culmination of all of this is this largest Blue Gene machine that was installed in the Livermore lab and mostly used for classified work. But I'll show you a graph that has some data that came from this machine. So. That's a discussion of the sort of introduction, and now I'd like to talk a bit about physics. The first is using Lattice QCD to try to learn more about the theory of the strong interactions of the quarks and gluons directly. We should be able to explain all properties of mesons, nucleons, nuclei as bound states of quarks and gluons, and be able to predict their properties. This is I guess now, it's a little bit old, a 10-year-old plot from the BMW collaboration where they're doing a full QCD calculation, some configurations at 0 quark mass, but a fair amount of extrapolation to 0 quark mass, but a pretty accurate discussion of the octet, the decuplet, and the nucleons. So in fact, Lattice QCD is quite capable of doing this, and it's now, I think, a really significant part of nuclear physics, at least in the United States. The Department of Energy has a nuclear and high energy part, and the nuclear part certainly owns the portion of Lattice QCD that is directed at nuclear physics. So Mark's talk mentioned effective field theory and low energy constants, and there's certainly a big program in the US to use Lattice QCD to calculate those low energy constants. Perhaps a little bit more a little bit more sexy is trying to calculate the matrix element for proton-proton fusion, which I understand is the first step in solar fusion. In principle, this has been calculated with the 800 MeV pion, and in not too many years, it should be something that is quite manageable using lattice QCD. There's a particular pi annihilation into 2 electrons with no neutrinos, a bit that goes into a more elaborate calculation of double beta decay, which is now a topic of lattice QCD. So one hopes as the future evolves that we can do more and more that are directly related to important questions about nuclei or about processes that teach us more about the standard model. So another example is this typically referred to as the Columbia plot of the up and down quark mass on this axis and the strange quark mass on this axis. If you make all the quarks very heavy, then you're basically in a pure gauge theory where the QCD phase transition that separates the confined phase and the deconfined phase is first order. If you make all the quark masses light, you're in a 3-flavor theory where there are also now a chiral transition will be first order, and certainly all of the lattice QCD calculations suggest that the physical point is really somewhere here. The strange quark mass is too possibly the up and down quark mass is too heavy as well. This transition for a SU3 flavor symmetric theory is actually quite a low mass, probably below 50 MeV. It hasn't really been found. This is some data from the Sequoia machine showing the fluctuations in the chiral condensate, which is a good way of discovering the location of the phase transition. These are rather large volumes. 32 cubed and 64 cubed by 8, varying the temperature by keeping the time dimension fixed and varying the coupling. So you can see a nice clear peak, and from that we could deduce the critical temperature, which was very much in agreement with earlier calculations using staggered quarks. So this is very mature, and one might argue that the QCD phase transition is fairly well understood. 2 different groups with using quite different methods. The second group, eager to prove the first group wrong, got the same thing. So the last part of my talk is focused on particle physics, trying to use lattice QCD to make predictions that will test the standard model, hopefully looking at places where the predictions of a standard model are so small that there's an opportunity for some other phenomena to be visible. So I'd like to talk briefly about the G-2 for the muon, the direct CP violation in K to pi decay, and a first principles calculation of a K long, K short mass difference. These, of course, are all calculations in the context of a standard model. We're using the standard model Lagrangian, all the parameters that have been determined to make predictions for aspects of each of these quantities. So the G-2 of the muon, as you know, is a very exciting topic right now. There's a sort of 4 standard deviation difference between the experimental and the standard model value for the anomalous magnetic moment of the muon. It's a very small difference, and there's now a very substantial experiment going on at Fermilab where they're going to improve the statistical accuracy of the experiment they expect by a factor of 4. And of course, it's to a large extent a different group of people, so it would be a very significant, even an experiment at the same precision will be quite meaningful. So this is a very accurately determined quantity, many digits, and although the electron anomalous moment is better determined because the muon is heavier, it is much more sensitive to physics at higher energies. The connection with lattice QCD comes from the fact that it's sufficiently high order in the perturbation theory. Quarks and gluons begin to appear in what would be initially thought of as a pure QED calculation. So there is the so-called hadron vacuum polarization, where the vacuum polarization loop here involves a quark, and then of course as many gluons as need to be emitted and absorbed from the quarks. This is all very low energy. There's no way you could do this treating the gluons per perturbatively, we have to do a lattice QCD calculation or an experiment. Here, of course, there is the R ratio, the E plus, E minus goes to hadrons, which actually measures the absorptive part of this graph and is the usual way that this is being done. The number I'm quoting here has an error which is somewhat smaller than that comes from the E plus E minus annihilation experiment alone, because it's actually a hybrid of a lattice calculation and the experiment, choosing the most accurate regions. If you integrate in position space for the difference, the separation between the two vector currents, you can combine the two in a way that gives you somewhat smaller errors. Here I wanted to focus on something that's a little more exotic. This is now an alpha cube term and contributes roughly on the order of the error. This is very hard to get from experiment. 3-photon scattering is certainly not a standard thing to do. And these, of course, are not on-shell photons. So the question is, can we compute something like this from first principles using lattice QCD? And I'm going to report on the work that a group of 7 of us at Connecticut, Nagoya, Riken, and Columbia and Brookhaven have been doing. So this is the PhD work of Lu Chang Jin, who graduated a year or so ago from Columbia. And this is supposed to be a picture that explains to you what we're doing. This is a muon line. It's treated in perturbation theory. This is the quark line, which is actually evaluated in the background of one of our gauge configurations. So we're going to evaluate this quark line over and over again with a variety of properly weighted gauge configurations, which has the effect of putting in all possible gluon lines in this diagram. And since all possible gluon lines would mess this diagram up, I have to ask you to imagine all the gluons that are being exchanged here. The photons are treated perturbatively. So we put in explicitly 3 photon propagators. This was Lu Chang's idea. And evaluate this by holding the point X, choosing the point here and the point here explicitly. So this is a combination of Monte Carlo average over the gauge fields and also stochastic sample over the position space integration points. And if we fix X and Y, then we can explicitly calculate the quark propagators with those points as sources, and we can integrate overall over this position. In fact, we integrate using a formula from Jackson that gives us the magnetic moment directly. And here we connect the photon loop and also do a full integration. So we have 4 space-time positions to sum over. We sum over 2 of those positions completely, and then 2 of them we sample stochastically. And this again is an important sampling. Lu Chang figures out where the amplitude is the biggest, and that's where we throw most of our points. And then of course we have to weight the result so that we get the right answer. The leading term is this connected graph with a single quark loop. We've also calculated this disconnected graph with 2 quark loops. There are a lot more graphs, but all the remaining graphs have, at least in one case, a single photon absorbed by a quark loop. So then the fact that the sum of the charges of all the quarks is 0 means that in the SU3 limit, at least, these will be suppressed. So those are a later task. The sort of data we get as a function of the separation between the 2 points X and Y that we are specifically choosing looks like this. We get the biggest contribution from nearby points, and in fact, we don't stochastically sample less than 5. We actually have it measured every single point here, and then, of course, averaged the whole constellation across our lattice to some degree. This is the disconnected part. With one more loop, it's negative, and there is a fair amount of cancellation. So the result we get without taking a continuum limit and without taking an infinite volume limit is the sum of the connected part plus the disconnected part, which is this number, which is actually about half the size of what's called the Glasgow consensus, the phenomenological result for this light by light diagram. We're, I think, going to do it. Well, we are doing a lot better. We now have continuum limits and infinite volume limits, and I hope within a few months have a not just a single number, but with a statistical error, but a number with a real systematic error. So we've, I think, succeeded in taking this light by light contribution to G-2 from being a troublesome uncertainty to something that will be understood certainly on the 20% level. Next, I'd talk quickly about k to pi decay. This now involves the full, all of us in the RBC UK QCD collaboration. So you can see we're getting a little closer to experimental physics here. There's a lot of technique that's needed to do this, and although not everybody is working on the k to pi decay, certainly most of the people in this list have contributed something that is important for it. So you might remember there are a couple of parameters that are measured to describe CP violation. The ratio of k long to k short, CP violating to CP conserving, decays into the two charged pions or to the two neutral pions. And these two numbers are typically expressed in terms of two parameters. Epsilon is the indirect CP violation. It measures the mixture of CP of the wrong CP in the k-long state. It is the same in both of these expressions and contributes the same quantity epsilon. Epsilon prime is the direct CP violation. It's related to the matrix elements, and it's different for pi plus, pi minus, and pi 0, so hence the changing number and the changing sign. The interest in this is, well, of course, CP violation is a place where the standard model has a problem, so it's fun to look at it. It's also these are very small effects, right? We have to involve a top quark, the CKM mechanism for violating CP is very indirect, and in the kaon system, the effects are quite small. So the indirect CP violation is 1 part in a million, and the direct CP violation is 1,000 times smaller than that. So one might hope that this is an opportunity for something else to show up that is not described by the standard model. But to realize that dream, we've got to actually calculate these two amplitudes in lattice QCD and figure out what epsilon prime is. So the two different isospins for the two pions are I equals 2 and I equals 0, and each of these describes a different amplitude. After the Watson phases are removed, we end up with the standard formula for epsilon prime. A2 and A0 should be relatively real after the Watson phases are removed, and this difference is an indication that they're not. So what we need to do is to calculate these explicit matrix elements in lattice QCD using the standard model. So a typical current interaction in the standard model, of course, would require exchanging a W. We don't have W's on in our lattice. That would require quite a bit smaller lattice spacing. So we make use of heroic work in the 70s that uses QCD electroweak and QCD perturbation theory to run the entire phenomena from the W scale down to the 1 or 2 GeV scale, where we can do a lattice calculation. So we're evaluating the 4 quark operators that represent the W exchange. And the typical Hamiltonian that we're examining would be if we use historical operators, it would be 10 different operators. The term here has the imaginary coefficient that gives us CP violation. And in principle, these Wilson coefficients have been determined. We can read them off of very long and elaborate papers, and that are so well written that we can actually change the input parameters a little bit if we wish. The 4 quark operators are and of course we need the CKM matrix elements here too. The 4 quark operators are quite elaborate. As we learned, we have yesterday, we have these delightfully named penguin diagrams in addition to the current exchange. So there's quite a zoo of different diagrams that we have to code accurately on the computer. But there is a significant challenge to calculating a matrix element like this. We would like to use lattice methods to calculate the matrix element between a kaon and 2 pions. And the kaon is pretty easy. You put in some combination of quarks and antiquarks, and we can create a kaon. And in our Euclidean space, we can wait some period of time for the excited states to decay and create a pure QCD kaon. The 2 pions are trickier, but we can exploit following ideas of Lucier and Lelouch and Lucier. We can exploit finite volume quantization. If we put two bosons in a box, if they don't interact, of course, you know what the free particle spectrum will look like. If they interact, the spectrum gets shifted a little bit. There'll be a series of discrete states. And in fact, if the box is bigger than the interaction radius, those shifts can be computed in terms of a scattering phase shifts, which is kind of fun. It's a little bit of an improvement on the statement that we can't talk about scattering. We actually can calculate low energy scattering phase shifts by looking at these Euclidean space energies of two pions in a box. We go a little farther actually and put boundary conditions on the quarks that guarantee boundary conditions on the pions, which make the, we don't have to go to such a high excited state. The most entertaining is using G-parity boundary conditions for the I = 0 state. So this is really rather elaborate. When a quark goes through our boundary, it changes into a quark of the other flavor, an anti-quark of the other flavor. So a U quark will go to a -D quark as it goes through the boundary. But we can manage that. And if we do that, the pions will satisfy G-parity boundary conditions, so they will be antisymmetric. And pions that satisfy antisymmetric boundary conditions in all three directions for a reasonable size box will have a lowest energy, which is the kaon mass. So the easiest thing is the delta I = 3/2 amplitude going to the I = 2 final state. Involves no disconnected diagrams. So this is a project that was finished a while ago, and we have a nice continuum limit, and we can compare the our calculation of the real part of this amplitude A2 with the experimental one, and the agreement's pretty good. We also have a value for the imaginary part, which is of course something that isn't known and depends on the conventions in our calculation. We also learned what the scattering phase shift is. We amusingly can examine the delta I = 1/2 rule. We get, in fact, an experimentally small value for the for A2, and it comes from a rather odd cancellation between two graphs that which have values very different from what factorization would suggest. And if you look at the value of the amplitude A2 as a function of quark mass, and then here plot as a function of pion mass, and compare it to A0 divided by 22.5, so that the two should agree, you discover that the A2 amplitude is very sensitive to quark mass, and this cancellation is kind of maximal at the physical point. And the error bar, the point with a large error, is actually our calculation of A0, but A2 is but the experimental value agrees pretty well too. I have a few minutes, maybe minus 2 minutes. Okay, so I think we can finish up pretty quickly. So the calculation involves a 32 cube by 64 lattice. We have physical masses for the pion, the kaon, and the 2 pion energy. And the result we get has a rather large error, but is fairly far from the standard model. It's within a couple of sigmas, so I don't think we can claim a deviation of the standard model. But we certainly have a lot of motivation to look at this a lot harder. And so the physical value is 16.6, and our value is 1.38, but with large statistical and systematic error. So we're busy improving the calculation, and hopefully even later this year we'll have a significantly better result with a lot more statistics. The k-long, k-short mass difference I think I don't have time to discuss, but so I think I would limit myself to maybe a single slide which says that by doing a second order weak calculation, integrating over the positions of these two locations of these two weak Hamiltonians, we can calculate an accurate result for the k-long, k-short mass difference without approximation, but it's a numerically very challenging task. So at the moment, we get a value compared to experiment of 3.483 of 5.8 with quite a large error. But this is an ongoing result, an ongoing activity, which we hope gets a lot better in the future. Thank you very much.
I assume that you produce a lot of numbers, and for those you cannot check with experiments, how do you cross-check your calculation? How should I trust you?
So that's a really good question. we typically have two independent calculations that are done by different people, and
Use the same program.
no, they write separate programs.
Oh.
Yes. So for the K to pi, for example, we have a postdoc and a graduate student who have both independently figured out what the contraction should be, compared their analytic results, and then written independent computer code and compared those results. Only one of the computer codes has to be fast. The other is just really being used for a check. But it's certainly a serious problem, and I think in the end, more than one group has to do the same thing.
I was wondering, how long do these calculations take when you do these in Mira or something like that?
I would say the typical job on Mira may use something like 100 million core hours and run on a portion of the machine for 3 or 4 months. So it's a significant activity. The QCD doesn't get a high priority on using these big machines, but we're always there. So any cycles that aren't being used, we can usually absorb. So in the end, I think that if you were to do some average over all of the supercomputing resources in the world in the open, you'd probably discover that the majority of the cycles are used by Lattice QCD. Although the owners of the machines won't admit that.
On the technological side, are you using already GPUs, or will the next generation be able to use GPUs? And that should be a big factor again.
Yes. So this, of course, varies a lot from one collaboration to the next. We've typically worked first with Intel, with IBM, and then with Intel. So our focus until recently has been on KNLs. But in fact, now the biggest machine is this Summit machine, which is a GPU machine, and that's just what we'll be running on in a few months. Yeah, so GPUs are a big deal, and there's a lot of GPU clusters that other groups in Lattice QCD use a lot.
Okay, let's thank again for the nice talk.